Gravitational potential energy. If I drop an object from a given height above the Earth, that object is accelerated toward the center of the Earth at a rate of g equals 9.8 meters per second squared. The acceleration of that object is due to the gravitational force applied to the object from the Earth. Since the gravitational force causes the object to be displaced in the same direction the force is applied in, work is done on the object. We call this ability of the gravitational force to do work on an object by causing it to fall the gravitational potential energy of the object. Gravitational potential energy is sometimes called energy of position because an object possesses this energy based on its position relative to the Earth. For example, if I stand on a box and drop the object from a greater height, does it have more or less potential for work to be done on it? The work we're calculating is the magnitude of the gravitational force times the magnitude of the displacement. The displacement will be greater if I drop the object from the greater height, so the work done is also greater. The object, therefore, has a greater gravitational potential energy when at a greater height. Let's say that we want to look at the motion of our object from this height, h initial, to this height, h final. Let's look at the work done by the gravitational force. The gravitational force and the displacement vectors point in the same direction, so the angle theta between them is 0. This makes the cosine of theta equal to 1, simplifying our expression for the work done by gravity. The magnitude of the gravitational force is equal to the mass of the object times g, the gravitational acceleration. So we can substitute this into our expression for the work done by the gravitational force. And the magnitude of S is equal to h initial minus h final. So the work done by gravity is equal to m times g times the quantity h initial minus h final. This equation is valid no matter the path between the initial and final heights. This is because it depends on the displacement of the object and not the distance traveled. Also note that the final height doesn't have to be on the surface of the Earth. Similar to the work kinetic energy theorem, this expression relates the work done by gravity on an object to the gravitational potential energy of the object. Expanding the term on the right-hand side, we can rewrite the expression in this way. These two terms on the right-hand side now give us the initial gravitational potential energy of the object and the final gravitational potential energy of the object. You'll notice that the term m times g times h is greater with larger values of h. So m times g times h is the gravitational potential energy of the object. Therefore, the gravitational potential energy of an object of mass m is the energy that the object has based on its position relative to the Earth's surface. Gravitational potential energy equals m times g times h. Since we're dealing with the gravitational acceleration on Earth, this expression for gravitational potential energy is specific to the Earth as well. The units of gravitational potential energy are joules, and gravitational potential energy is a scalar quantity because it only has a magnitude.